Oh, thank you so very much. That's a very kind introduction, and it's my great pleasure and honor to be a plenary speaker at the AESC. I always enjoy the meetings and get a lot out of it. Unfortunately, we don't have the same kind of personal interaction that we would normally have at in-face gathering, but nevertheless, I hope you will be able to enjoy the presentation I have today. So this work stems from 2 decades now of traipsing around in the Pilbara, and our work has gone from really identifying the sticks and stones of rock formations into really looking at things in a more holistic and systematic way. And we've been fortunate enough to engage with planetary exploration groups. And so this talk will sort of try and weave a few of those things together and give you an idea of what we're thinking of for maybe the next step in the exploration of Mars, as well as what's happening at the moment. So a second genesis really refers to finding a rock band on Mars. Well, this is a very oblique reference for those of you who were born sort of before the 70s. A rock band called Genesis was very popular. And of course, we are looking for signs of microbial life on Mars, probably not complex guitar-playing eukaryotes. So moving right along, we have, of course, an incredible abundance of options if we think about looking for life elsewhere in the solar system. And I've put up just a few of the nearest planetary neighbors. And what's interesting is that they have very different chemistries. So the gas giants, of course, have ammonia clouds. Venus has a CO2-rich atmosphere. There's the sulfur volcanoes of Io, the methane lakes on Titan, and of course, the water worlds of Enceladus and Europa. And there's the red dust and rocky planet of Mars. Where would be the best place to go and look for life? So much choice. To date, there's really been a strict adherence to the idea of follow the water. That was really the main guiding principle for NASA and thinking about the habitable zone, because all life on Earth needs water to survive. And if you look at the size of a solar mass here versus the distance of planets away from the sun, there's this habitable zone, which is basically where there's liquid water. Earth falls within that. Venus is probably a bit too close, so it's got a steam atmosphere. Mars, quite distant now, very cold, but there's evidence that it did fall within the habitable zone in the deep past. So that idea of follow the water makes planetary bodies like Enceladus and Europa quite exciting because they're covered in water ice. And in fact, we know that they have liquid water in the subsurface. And so given that there's water there, then yes, these could be an interesting target to search for life because they have potentially habitable environments. And there are 2 different types of missions that are being planned for Enceladus. One is to land a little rover that's actually a drill in a submarine that will drill through the ice and then go swim around in the subsurface and look for vents of hot water coming from the planetary interior and see could there be signs of life there. Another approach has been to actually have a small spacecraft fly through the water vapor jets that are coming out of Enceladus and using a beautiful little machine called nanopore sequencing, look to see if there are complex organic molecules such as DNA that could be an indicator of life. But the thing about water worlds and the thing about the follow the water kind of exploration is that's good for life that already exists. But one of the key take-home points I want you to think about now is that there's a very complex story about getting life started. And those conditions may not be the same as conditions that would allow life to get to live. And this is really because even the most primitive life is an incredibly complex machine. It has a triple layer membrane. It has a cytoplasm that's compositionally distinct from the exterior. It's got, of course, the DNA, it's got organelles, it's got all kinds of functional activities that are, coherent in a living microorganism. And these need water to survive. But the really critical question in terms of thinking about space exploration of life is what were the conditions required to get life started? Now, we don't actually know. I'm going to say that right up front, but we have some ideas. Part of the reason we don't know is that the pathway, the roadmap to get life started is unbelievably complex. This idea of abiogenesis, of coming from organic molecules brought in by solar system materials like meteorites, and then combining them in this really complicated way to get RNA and DNA and then encapsulation and self-replication, is millions of steps, possibly even trillions of reactions. We've gone partway down that path with some experiments. This is the famous Miller-Urey experiments from the late 50s, where they undertook simple experiments in a lab with a primitive atmosphere, some water, and a spark discharge, and they were able to make some simple amino acids and other organic compounds. So this is using, if you like to think about it in very ancient terms, water, air, and fire to develop a certain level of complexity. And that's very exciting research, and certainly was a major advance in our thinking. But it's limited because it only gets you so far. Now, the ancient Greeks, they knew that there were 4 basic elements of life. You needed earth, so a rocky planet. You needed water, air, and fire. And more recent studies have shown that, to get very complex organic molecules, you need not just the basic elements you can get from water, air, and fire, but you need a contribution from the earth in terms of trace metals and trace elements, such as boron. This paper by Naveau and others, and also by others in Steve Benner's group, have shown that no other mineral anion is as satisfactory as borate to stabilize the formation of pentoses. So here's boron in one of these complex organic molecules. Other studies have shown that you need other trace elements, such as zinc, molybdenum, potassium, sodium. And this starts to really limit our ideas about where you can go to search for life elsewhere. It's not just the presence of water. You need to have these other elements and a mechanism to concentrate them to make this complex organic chemistry in the lead up to life. Now, presently, the community is divided between an origin of life at deep sea hydrothermal vents, and actually we're in a paradigm shift at the moment, where the community is now starting to really favor the idea of an origin of life in hot springs on land. Now, both of these systems generate complexity through interaction between hot circulating fluid and rocks that transport elements to the surface and make interesting chemistry. The difference is the temperature and also the fact that in the deep sea, the conditions are permanently wet, whereas on exposed land, they are able to undergo periods of drying. And as I'll show you, this can become extremely important in thinking about the origin of life. So these systems generate chemical complexity through that water-rock interaction. In fact, hot springs have an additional feature where they can have air-rock and air-water interactions. So you actually have 3 interactive media there. Now, just to summarize briefly, the idea of origin of life at hot springs really stemmed from the discovery of deep, very primitive microbe communities that lived on these hot springs and got their energy just from chemical energy. And the idea was that there were these very steep thermal gradients across the margins of these chimneys where you could get, transfer of elements back and forth and reaction spaces that would generate interesting chemistry. This idea also fit with sort of early knowledge about the tree of life, where at the base of the root of the tree of life, it was understood that hypothermophiles, meaning organisms that were maximal in terms of their metabolism, thrived at temperatures of 90 degrees or more. So this idea of hot, deep life based on chemical energy really took hold and has been the dominant paradigm for the last 30 years or more. But our understanding of the tree of life has changed over time. And in fact, whereas now the hypothermophiles are still there, in fact, the most primitive organisms turn out to be mesothermophilic, or liking cooler temperatures, even down to temperatures such as 20 degrees. So that is maybe a bit of a shift. And people have also thought that there are interesting reactions that can take place under slightly cooler conditions, off-axis hydrothermal vents, and white smokers, where there's alkaline chimneys, still generating interesting complexity in terms of water-rock interactions. But there's a problem with both of these sites, and it's known as the water problem, and it's been known since the 1970s. Any reaction that takes simple organic molecules, like amino acids, to make proteins, or carbohydrates to make more complex polysaccharides, or even the reactions to form the nucleic acids, DNA and RNA, you'll see that all the reactions required to bond those molecules together kick out water. They're called dehydration or condensation reactions. And in fact, complex organic molecules break down under permanently wet conditions. And so this is why it's called the water problem, is because the complex building blocks of life require the ability to dry down to cause the elements to bind together. Dave Deamer, who's a bit of a godfather in the origin of life field, in his beautiful book called First Life, published in 2011, says, you can heat a solution of amino acids in water forever, but no polymers will be produced. On the other hand, polymer synthesis can occur if the amino acids are in a dry state. And this is a critical part. The source of energy that binds those molecules together is that water molecules have the potential to leave the system. So there are other problems with oceans. So that we know that they're too wet, they're too salty. Salt is bad for making a lot of things in complex organic chemistry. And they're dilute homogeneous reservoirs that disperse element concentration, not make them more available. And so now people are starting to think that oceans may not have been the setting for the origin of life. Instead, we've been part of a group, like I said, a paradigm shift that the community is now starting to think about an origin of life on land. We published this in Scientific American in 2017. We were by no means the first. In fact, Charles Darwin in 1850s suggested that life may have started in some warm little pond, a phrase I'm sure you're all familiar with, a very insightful thought about where life might have gotten started. The real benefit of an idea of life in hot springs on land is this idea that they can undergo wet-dry cycles. I don't know if any of you have been to any of these pools. This is Grand Prismatic Springs in Yellowstone, but you can see many of them in New Zealand and many places around the world. But they ebb and flow, they rise and fall, there are geysers splashing, and if you look at the video, you'll see that the margin there becomes wet as the geyser erupts and then dries out. And this is very exciting in terms of generating complex organic geochemistry. We also know, and here's Dave Deamer again, pouring a solution of relatively simple organic materials and lipids into a relatively neutral hot spring. And they found that those lipids automatically develop into these beautiful little vesicles with membranes, and they have the ability to concentrate organic matter within them. This dye here is showing concentrated organic matter within a lipid bilayer vesicle that is starting to look like protocells. So that's very exciting, and this process does not work in salty water. Those lipid vesicles just disperse and become very complex and break down. And then, of course, we know that distinct springs can concentrate different elements. They can concentrate sulfur, arsenic and gold even, boron, iron, organic matter. They're extremely complex, extremely varied, but they can concentrate elements and make those available for prebiotic chemistry. And what I love about hot springs is that they occur in fields, often in terms of tens or even hundreds of pools, very close to each other, with radically different chemistry juxtaposed within tens sometimes even just a few meters. In this example from Rotorua in New Zealand, we can see the neutral Champagne Springs pool, which is bubbling away with CO2 and is about at 75 degrees Celsius. And then in the bottom left corner, a pH 2 acidic pool rich in sulfur. And the lovely thing is they can exchange their information and their chemistry across these slopes. So you can generate extremely chemical and energetic diversity. In fact, hot spring fields are the most geologically complex places on Earth. And if we think about that roadmap to chemical complexity, that generates excitement. And so our idea, which we put forth in that Scientific American experiment, is that you can mix and match material and generate pools of greater fitness. And so by mixing and exchanging materials with different pH, different temperature, different concentrations of elements, you generate complexity, leading to innovation pools that have greater fitness. Now, this is taken directly from biology, but can apply equally to mixing any components and works for prebiotic chemistry as well. And so this has really led to a hypothesis about the origin of life that was published first in Scientific American, but now much more detail in Astrobiology in 2019, that organic matter coming in from space and being delivered down into a primitive crust, maybe even before the oceans rained out of the atmosphere, started to get concentrated in pools that had chemical variation. Those systems underwent wet-dry cycling to generate these protocells that became increasingly more and more complex with internal organic matter. Of course, we don't know all the steps, but the hypothesis is then that they formed in freshwater and had to adapt later to the oceans as life took hold. And so, could this model apply to early Earth, or is this really only something that applies to the modern day? So this is now going back into my area, and I want to take you back 3.5 billion years to when Earth was a very different looking planet. If I was able to time travel and look at a view of early Earth, and I was able to sit on a pier sipping a pina colada, the oceans would have appeared green because they would have been full of dissolved iron. The skies would have been orange, high in CO2 and methane and other reducing gases. And any exposed land masses would have been black basaltic lavas like you find in Hawaii or Galapagos, straight from the mantle. None of this differentiated light-colored crust. And so if we were able to view Earth from space, we would have seen a green ball with some black exposed continental masses and fluffy orange clouds. You can see the level of my skill of illustrations. But Earth would have looked like an exoplanet. It would have looked like a different world. So what does that look like? What can we see if we travel back in time 3.5 billion years? Well, we can see that by going to the Pilbara Craton in Western Australia. It has extremely well-preserved ancient rocks in an area known as the North Pole Dome, where we have the 3.48 billion-year-old Dresser Formation exposed in gently tilted cross-sectional view, where we can see the underlying hydrothermal system that provided large-scale fluid flow and chemical transport of material to the surface. We can see the bedded sedimentary rocks, which include both clastic and chemical sediments, and of course, the famous stromatolites, the oldest, most convincing evidence of life on planet Earth. And we've been investigating this area for a long time now. And the depositional environment really looks very much like this. This is an area where in cross-section, it's fed by a magma chamber we can no longer see, but there were volatiles being developed to the surface, driving hydrothermal circulation that caused extensive alteration of the footwall and liberated elements and transported them to the surface, where they became concentrated in a restricted basin, pretty much a volcanic caldera lake. One of the best analogs that we can envisage for this process is actually from Tonga, where a large volcano, probably 4 or 5 kilometers across, has a caldera lake with little islands, hot springs, and stromatolites growing on the side. This is very much what we see in the rock record from 3.5 billion years ago. Now, my student Tara Jokic found a little rock sample that we sliced open, and it has these very distinctive textures, these beautiful microlaminations, botryoidal features, troughs, little slumps, and overlapping patterns on layers with truncations. These are all textures from this slice 3.5 billion years ago. And they have one-to-one correlations from modern hot spring deposits from a geyser. This is a rock known as geyserite. It's exclusively formed by splashing hot water. And we analyzed this black-white layering here at very fine scale, sub-millimeter scale, and we found that it consisted of alterations of titanium-rich and then aluminum and potassium-rich laminae. And we know that this occurs in hot spring alteration of basaltic crust. Here's an example from Iceland, which has silica, anatase, and kaolinite, exactly the minerals we have 3.5 billion years ago, and it also forms montmorillonite. Now, montmorillonite is extremely important in prebiotic chemistry because it can generate concentration of organics and help catalyze RNA. So we're starting to get hints that there were rocks and environments that were important for prebiotic chemistry. And of course, a geyser indicates that you had wet-dry cycles that can help make complex organics. We also found a little unit here, just shown as this tiny little wavy crust. And when we started to analyze it, we found it was full of all these little green crystals. And these crystals turn out to be tourmaline that are rich in boron. And we analyzed their boron isotopic composition. They were at about -13 in this area of the green, right under the area of non-marine evaporites. Nothing like seawater, which is up at +30, +40 per mil. So these are clearly boron-rich horizons that formed on the surface, confirming that idea of hot springs and also about concentration of a prebiotically important element right there 3.5 billion years ago, just as there are boron-rich springs erupting today in India. So we started to look at this, and we've developed now this scenario for the hot springs within the Dresser Formation, where there's geyserite, we've identified silica terraces, and we can identify that there are all these different elements being brought to the surface and making them available for complex chemistry, including the presence of kaolinite and probably montmorillonite in the altered footwall. And of course, there's wet-dry cycles. So we really feel that in terms of thinking about the origin of life, based on our knowledge of modern examples and ancient examples, that this is the way to go in terms of thinking about the conditions required to get life started. Wet-dry cycles can form those lipid vesicles. We can concentrate not only the classic prebiotic elements for organic geochemistry, but also the trace elements required to catalyze reactions. There's a variability in terms of pH, generating complexity, and those can exchange chemical information. So in fact, if you think about it in terms of a holistic planetary cycle, hot springs could be the first as well as the last outposts of life if conditions change and alter over time. So now I want to take you onto an astrobiological journey. What are the implications of this finding? Well, our implications would actually suggest that the water ice worlds of Enceladus and Europa, which are currently, the subject of a lot of excitement for astrobiology, they're actually perhaps not so interesting because there's no indications that they ever had an exposed rocky surface. And so maybe life could never have gotten started there, even though the conditions now might be habitable for existing life. Same for Titan. Huge amounts of carbonaceous matter, there's methane lakes, and lots of potential for generating interesting organic molecules, but without the complexity of rocky minerals and others, well, maybe that's not so interesting for getting life started either. Well, Mars, we know that it's got a rocky substrate, and we know in the past it had evidence of water. So initially I was not all that excited about Mars, but I've become much more excited as I've gotten to know more about it. Of course, the first impressions are not so fantastic. This is what, the landing site of Mars was like for Spirit when it landed a couple of decades ago now, and in fact is representative of much of the surface of Mars. It's dry, rocky, dusty, not much hope for life getting started there at the moment. But of course, we know that in the deep past, there's lots of evidence for water. There are large-scale river channels that look very similar to those on Earth, with anastomosing braided rivers, deltas, all kinds of features. We know that there are sedimentary deposits that were water-laying because these are sulfate minerals formed through evaporation of fluids. There's widespread evidence of clays on the surface that are only formed by the interaction of rock with water. And of course, the famous Martian blueberries, which we know again from analogs on Earth, form as a result of interaction between fluid and iron-bearing rocks, concentrating the iron into these little pelloids. Now, the other component that's important is we know that Mars had a very active volcanic environment as well, providing the opportunity for generating hot springs. And in fact, here at Nili Patera, Skok et al. Identified from orbit these bright areas as being made of opaline silica, the same material we find in hot springs on Earth. And the suggestion was these could be actual hot spring deposits. Here, what looks to be actually coming out of a small mound on the edge of this little volcano and forming deposits around the edge, just like we see in hot springs today. Now, importantly, NASA has already visited a place where there are opaline silica hot spring deposits. The Spirit rover, and here's its track, visited an area known as Husband Hill first, and then it came down to an area known as Home Plate. And in the area around Home Plate and on its traverse, they found indications of hot springs in two different forms. They found sulfur-rich soils in many different places, as you can see. It was originally found through scraping through the dust and fine silt cover of the wind-blown aeolian material at the surface, and was found in situ to be composed of up to 36 weight percent sulfur. But more importantly, they found physical hard rock evidence of opaline silica deposits in a number of places around this Home Plate feature, which is a little circular depression filled by volcaniclastic ash deposits. So in the areas shown in the white dashes is where they found opaline silica. And with Spirit, we have the wonderful opportunity to look at very close-up images taken by the cameras, and we can see geology. We can see a thinly bedded unit. We can see those little nodular deposits of opaline silica, and we can see overlying lapilli tuffs. It really is, for a geologist, pretty exciting. And we can even understand a bit of the history of how that has changed over time. We can clearly see the erosion and downslope progression of lapilli coming from weathering of this big block here, covering the other units. We can identify deflation of units by gravity going down slope. This is a silica nodule lying on the underlying bedded tuffs, but clearly displaced. And here's another deflated one. This is a deflated ash tuff from this block. And we can actually start to identify the units that are in situ and draw geological contacts and develop a stratigraphy. In this case, we can identify that what's called this buff-colored platy unit, but actually is a sulfate-altered fine-grained ash deposit overlain by these nodular silica deposits that form parallel to the bedding, and then the overlying volcaniclastic rocks. And if we do that kind of analysis, this is work that I've done when we were advocating for the Perseverance rover to go back to Columbia Hills, we can actually map a series of folds, and a coherent stratigraphy that wraps around the home plate centrocline. And that gives us a geological history. We know that the opaline silica is a stratigraphic unit, and that gives us interesting ideas about the context and how that unit formed. It must have been part of a much more widely distributed unit for it to be preserved as it is. Now, the reason we got very excited about this, and this is really led by a colleague of mine, Steve Ruff at Arizona State University, who was on the Spirit Science team, is that the outcrops of opaline silica, this really unusual nodular structure with all these little digitate forms, meaning little finger-like protrusions, very unusual. And what Steve has really contributed is that he showed that up in the most Mars-like environment on Earth, up in the very high Andes in Chile, are hot springs that are forming exactly, at scale, texture, everything else, the same type of digitate nodular opaline silica deposits. These form because of the high evaporation under those very high altitude dry conditions. And what's exciting is that, here's a picture from Mars showing this sort of, hand of God kind of texture with those, curved digitate features. And here are the same kind of features at the same scale from El Tatio in Chile. And when we look at these structures on Earth and we break one off, we can see they're finely laminated. And if we do high resolution analyses, we can see that there are trapped microbes in here, beautiful cyanobacteria filaments, both vertically distributed and horizontally distributed, and tuned in opaline silica. And in fact, that digitate structure is formed because of the activity of microbes. And so Steve has suggested that maybe there's actually a biosignature we've already seen on Mars. And given the fact that hot springs are exciting, we think that's a great potential. At the moment, both the European Space Agency and NASA are heading towards places where there was flowing water. For NASA, as we heard from Indriani, the Perseverance rover is going into the Jezero crater and will be inspecting this beautifully preserved delta, which is at the end of a beautifully anastomosing river that spills down the lip of a crater and then debouches onto the crater floor with all these sediments. The target there is to look in clays at the toe of the delta for concentrated organic matter, if there is any, and also along the rim of the crater where there's been identified higher concentrations of carbonate, maybe at the lake edge, maybe with stromatolites, who knows? Those are the targets at Jezero, amongst many other things. The European Space Agency was due to launch this last year, but has been delayed till 2022. They're going to ancient lake deposits in Oxia Plana. We're excited about the potential for going to Columbia Hills, collecting a piece of this digitate opaline silica and bringing it back to Earth for analysis. And in fact, we have started planning a mission to go and do exactly that with the Japanese Space Agency and colleagues from the University of Okayama, including scientists from many different institutes around the world. We're starting to develop a disruptive kind of technology base for developing a light and nimble mission, which would go collect a very small piece of sample material and bring that back for analysis. No big, large, fancy rover. We know exactly what we want, exactly where to go, and bring that back to our labs to look for signs of life. We think that hot springs are an extremely exciting target to look for signs of life on Mars. And that's really how this idea of looking at a deep time environment, thinking about conditions, how that applies not just to habitable environments for life that already exists, but thinking about the conditions required to get life started, all combine to inform us about thinking how to search for life elsewhere. And so I'd just like to take this opportunity then to thank my colleagues, students, and people from around the world and funding agencies who have helped support this research over many years. And give a shout out to the Pilbara, which is still my favorite place in the world, because we're always continuing to learn more and more about how complexity was generated in deep time. And I'm going to stop there. So thank you very much.